this recording, especially since we're missing a couple of people. Maybe they'll need the recording. Okay. We're hopefully going to mostly wrap up logarithms today. There might be a little bit left over for the Friday video, but I think we're going to get most of it done today. So we're going to talk a little bit about domain. This is the area we haven't talked about yet, hardly. So if you'll remember, we got the graphs for logarithms the other day on Monday, and we said exponential functions, remember they had a horizontal asymptote and they went up. Logarithmic functions have a vertical asymptote at x equals 0, right? And then they come along beside that vertical asymptote and they go like this. So there's always that point 1, 0. And then there's always the point, I'm going to do log base 2. So there's the point 1, 0. And then because the base is 2, there's going to be that point 2, 1. Right? Those points are always going to be on there. And then we just say, okay, that asymptote acts like a magnet. It draws the graph toward it and downward in this case. So all of my logarithmic functions look like something like that before we start shifting things around, right? Okay. Hey, Avery, I see you. I got you, Amanda. So I still don't see Carly. No, okay, no problem. So they all look like this before I start shifting around, and they are all one single piece. So these are not piecewise functions or anything like that. What that means for us is this: we have this vertical asymptote going right here. We know we can't cross it. All of my graph is on the right-hand side here. Is there going to be anything over here where my x's are negative, like -1, -2, -3? No, because this vertical asymptote is a do not cross, right? We're never going to cross that line. So all that stuff on the left-hand side, those are just not going to have a graph on them. This is my graph. We're done. Okay. So the thing that your homework is going to start asking you about is, what about the domain? And what about the range? Okay. So, and these are questions from exam 1, but they come back every time we have a new function to deal with. We kind of want to talk about domain and range, what's going on. So domain, if you remember, that's always your side to side, your x values, right? Okay. So in this one, I see that I'm going to come down to the 0, x equals 0, right? We always start on the left-hand side, read left to right. So we start here at the x equals 0, but I'm never actually going to touch the 0, right? So, because that's an asymptote, so do not cross. It's a bad spot in my domain. So instead of a hard bracket there, I'm going to have parentheses. So it starts at the 0 and does everything that's above it. I have a 1, a 2, a 3. I go all the way out here to x equals 1,000,000, right? So that means this arrow is telling me all the way to the right. So it's an infinity. And remember that infinities have parentheses. They don't have hard bracket. All right. And then there's the question, well, what about the range? So x's are my domain, y's are my range. And so we always read that one from the bottom go up, right? So how far down does this arrow point me to? All the way, right? Okay, so it's all the way down to starting at the negative side, right? So negative infinity. And then this arrow goes to the right, but it's also creeping upwards at the same time, right? It's going to the right and up and right and up and right and up. So how far to the up does it go? All the way, right? So negative infinity to infinity. Okay. And the deal with the domain is that the asymptote can move, right? Whenever I start translating things. So if I shifted this whole graph to the left too, then it wouldn't be 0 here anymore, right? It would go left 2 to the -2. Okay. So the domain is going to change depending on whether or not I shift this graph around. Okay. Range is going to stay the same. It's always negative infinity, infinity. We're going to have all of those guys, no problem. But the domain gets to move around depending on what happens with the graph. Okay. All right. So there's a lot of, with logarithms, application problems. So we haven't seen those yet. So I want to get a little bit of that in. For instance, there is something about earthquake intensity, and the example says that you have a magnitude called an R on the Richter scale. The Richter scale tells me the magnitude, or we'll say strength, of an earthquake. Okay, so you'll hear people say, oh, there was an earthquake out in California the other day, and it was a 5.0 on the Richter scale. Okay, that's pretty strong, but it's not as strong as it gets, right? So basically, this is a device that measures how much the Earth is moving whenever we have these things. And there's a formula for it, okay? And that formula is given with logarithms in it. So it's R equals, and you will not have to memorize this. If you need to use it, it'll be on a test somewhere. Logarithm of I divided by I sub 0. Okay. And what it says is I sub 0 is the intensity of a barely felt 0 level earthquake. And the I that we're looking for here is the intensity of the one that the earthquake that's currently happening or that we're examining. So the problem says there was an earthquake that destroyed San Francisco in 1906. There was an earthquake in San Francisco. It knocked down all kinds of buildings and they had to rebuild. Okay. So in 1906, there was an earthquake and it was 10 raised to the 8.3 times as intense as a 0 level earthquake. Well, 0 level basically means everything's sitting still, right? There's very, very little movement going on in the earth. Okay. So they're like, what is the Richter scale? That's what they want to know. So what is the R? Find R. Scoot here. All right. So that's what they want to know. So find R. So it's not so bad. What we have to do is we have to be able to relate the one we're talking about, the earthquake that's in San Francisco, with a normal 0 level earthquake. Okay, so the formula is R equals the log of, and the intensity of this particular earthquake is 10 times as intense as the 0 level. Well, the 0 level is here, right? And this is our earthquake that we want to talk about. So 10 to the 8.3 times I sub 0. And it's going to be divided by I sub 0, right? Okay. But whenever you look at that, you go, oh, well, clearly I can cancel out those I sub 0s, right? Those can go away. There's one on top, one on the bottom. And so this is just going to tell me, take the logarithm of 10 to the 8.3, okay? And they're not writing a base. There's no log base whatever here, right? So we have to think about that. What is this base right here? When they don't write one, it's a common logarithm, and that's always a base 10, right? Okay. So we can ignore the base there because it's always going to be a 10. That's what they're doing. That's why they're ignoring it. But it's going to come in handy for us here because we've got a base 10 here and we've got a 10 raised to the exponent here. So if we can kind of start using some of our logarithm rules, then we know that the log base 10 of 10, we can do something with this exponent up here, right? Remember, I've got an exponent raised to an exponent. The rule for that was multiply. Exponent to an exponent. we multiply. Okay. So I want to multiply this exponent by whatever's going on with this whole big old logarithm thing, right? So I'm going to pull it out in front. 8.3 log base 10 of 10. Okay. I'm going to pull that 8.3 out in front. That's being multiplied, right? 8.3 times the log. Yeah, I'm going to absolutely pull that out. And then we just need to think to ourselves, oh, there's a little logarithm property we had where we say, what's the exponent? 10 raised to some exponent gives me a 10. This guy is equivalent to what? That's a 1, right? So all of that will go away and it's just a 1. So this is really R equals 8.3 times 1, but we know that's just 8.3. So if they want to talk about that 1906 earthquake in San Francisco, then they would use these logarithms and they'd come up with this reading and they'd say, hey, that earthquake was an 8.3 on the Richter scale, which is actually really high. Okay, so absolutely that guy's high. So you're going to see some application type problems like that. It's just a matter of being able to read the formula. You don't have to memorize them and then being able to utilize it. Is that all right? Okay. All right, I think the last thing we need to talk about with logarithms is the natural logarithm. Last time we got in the common logarithm. And I mentioned that sometimes we have a logarithm with the e for a base, right? So we've got log base e of x equals some y. We don't know what that is. And you can always write it just like that if you would like to, but what you're going to find is like on your calculator, there's a special log base e button, okay? And so there's a special way of writing it, and it's ln of x equals y. Okay, so just as a definition, so to speak, you want to say the natural logarithm log base e of x is equal to the ln of x. Just those are equivalent. Okay, so what you're going to see is they start using ln of x a lot, and your calculator has a button that's specific for ln of x, and that ln stands for, like it was a French thing, logarithm naturel or something like that. Okay, so it's a natural logarithm. But the nice thing is these guys, they work just like everything else that we've been doing. So even if they have an ln, it doesn't matter. They're still, it's log base e, and all the stuff applies just the same as what it has been. So we're going to have stuff like, okay, can you take the logarithm, the ln of certain things, and use some of our properties, right? So here's an example like that. We've done some of these equations already. I'm just going to show you one with a logarithm, natural logarithm in it, so we can see what's going on. So what happens is we'll have something like this, an example. E to the 2x equals 5. E to the 2x equals 5. And it'll say solve for x. Okay, well, I'd love to solve for x, but there's a problem. The x is in the exponent, right? It's way up there. So when I look at that, I say, ooh, this is going to be kind of a pain to get out. But I see I've got the base is e. I've got some exponent up here. On the other side, though, I can't change this e into some power of 5 or something like that. So that's not going to work for me. So I'm just going to have to keep it as the base is e. But when I want to get that variable down out of the exponent, the answer is you need to take a log. Okay, so we're going to log base e this guy. Okay, when I do that, so here's the take the log of both sides. When I do that, I'm going to take the log on the left-hand side, but this is an equation. Everything's got to be equal, right? So I need to take the log of both sides. It's just like if you were multiplying by 5 on both sides or something like that. You always have to keep it balanced, keep your equation balanced, and do the same thing on both sides, okay? So this is what it's going to look like. I'm going to take the ln of e to the 2x on the left-hand side. And on the right-hand side, I'm going to take the ln of 5. Okay. And then we're just going to say, okay, well, now that I've got a logarithm, can I do something with it? Remember my goal. My goal is to get the x completely by itself. And right now that x is up in the exponent. So the idea of taking the log is now I can use that rule we just used a second ago. Now I can say, hey, I've got an exponent. This log is an exponent raised to an exponent. I can multiply those. So I'm going to pull this guy down in front. Okay. So a lot of times when you do this, the idea is get that exponent down, get that exponent down. Well, the way we do it is we take the log and then we write it out in front, and remember that's multiply. So it's going to be 2x times the ln of e is equal to the ln of 5. Okay. Well, again, we got to go back to those little properties that we know. Log base of b, okay, equals something. Basically, what we're saying is the base raised to some exponent gives me the base. Well, it's got to be base to the first exponent equals base, right? So this guy over here is going to be a 1. Okay. So anytime I see, hey, I've got a logarithm and it's got a base and I'm taking the log of the same number, those are going to basically go away, and that's a 1, right? So this is log base e of e. They cancel basically, okay? The log base e of the e, those are going to go away. This guy right here, ln of e, is going to be a 1. And again, that's why we took the ln, because we want that guy to go away. We want to just be dealing with the x's if we can, okay? So that's a 1. So now this becomes 2x equals ln of 5. And we sure know how to solve for x here, right? We're multiplying by 2, so we're going to divide by 2. So both sides get divided by 2. These go away. X equals ln of 5 divided by 2. And I'm going to say leave that just like that, okay? If for some reason, like in Math Excel, it says, no, we need you to give us a decimal value, then okay, you can probably punch that in your calculator, no problem. I'm looking to see if I've got a calculator. I might not have brought it with me today. I don't think I brought my calculator today, I'm sorry. But you can punch that LN button. It's right next to or above or below the log button. You can punch it and get a decimal here, but I feel like you're going to have more space for making mistakes. So just keep the ln of 5, divide by 2, and that's your answer. That's the exact answer rather than a decimal approximation. Okay. So we get the x by itself, we're happy. Is this okay with everybody? Missing some of my peeps, I see. Everybody's all right. Okay. Well, that's the idea behind what's going to happen here. So that is the next information. So in your Math Excel, I feel like you can now do 4.1, 4.2, and 4.3. We've done all 3 of those sections, and we're starting in on the 4.4. Okay. So homework, yay, get those done. 4.1, 4.2, 4.3. So the next section is called logarithmic and exponential functions. And it's really about solving them. Solve these equations. That's what we're after. Okay, which means just like it always has all semester, get that x by itself or whatever the variable is. We're going to get that guy by itself. So some of these we already kind of looked at a little bit, changing for exponential functions, changing them so they have the same bases and stuff like that. We did a little bit of that the other day. But I want to do one where we've got an exponential function similar to what we just did. and there's no changing the bases. So I'll do one that's the same base, just so we kind of get, oh yeah, I remember that. And then we're gonna do some other kind of weirder stuff. So here's our example. 27 to the x plus 3 equals 9 to the x minus 1. Okay. All right, so if we remember the other day, we did some of these and we said, oh, I can look at 27 and I can say that's 3 times 3 times 3. And I can look at 9 and I can say that's 3 times 3. So hopefully we can say, okay, we can rewrite these with 3 as the base. 27 is 3 to the third. The 27 is being raised to the x plus 3 power. And 9 is 3 squared. And that's being raised to the x minus 1 power. Okay. So if I can rewrite those so that they have the same base, then I can use all of those exponent properties that we like. So remember, whenever I have a base raised to an exponent, and that guy's raised to an exponent, this is exponent to an exponent, I multiply, right? Okay, so this is going to be 3 to the 3 times x plus 3, and we'll get that simplified in a second. And that's going to be equal to 3 to the, and same thing here, exponent to an exponent, we multiply, 2 times x minus 1. Okay, now we know that that stuff's going to simplify. So this is 3 to the 3x plus 9. All right, multiply that through, distribute your 3. Okay, and on the other side of the equal sign, we've got 3 to the, and this is 2x minus 2. Right? So when I look at that, now I've got a base to an exponent equals the same base to an exponent. And we did this the other day, right? So we said, oh, whenever you've got the bases are equal, then you know the exponents must be equal. So I can take those guys to the side and work with just those exponents. So I know 3x plus 9 has to be equal to 2x minus 2. Because if these are equal, to keep everything equal, the bases are already the same, then the exponents have to be the same. And then this just turns into solving a linear equation. So that's not too terrible. Subtract 9 on both sides. Subtract 2x from both sides. These go away. I have 2x, sorry. 3x minus 2x is 1x is equal to negative 2 minus 9 is negative 11. X equals negative 11. Okay. And of course, you can check your answer and make sure it works and all that good stuff. So that's the way we dealt with these exponential functions on Monday. Okay, so if we can rewrite them with the common base and we're happy working with their exponent properties, then these are great, no problem. Okay, but they're not always going to be so nice and pretty for me where I can set them up with the same base. They're not all going to have the same base, in other words. So the other examples start being more complicated. So here we go. What if it is 4 to the x equals 15? Okay. And I look at that and I say, oh, it's definitely exponential. The variable's up in the exponent. I need to get it down. 4, I could rewrite 4 as like 2 squared or something, but 15 is not going to work that way, right? It's 3 times 5. So it's not a power of anything or anything like that. So this is one like what we did just a second ago. So I'll look at it and I say, oh my gosh, inside of here, they don't have anything in common. I can't rewrite them with the same base. Let's take the logarithm of both sides. So that's what we did just a minute ago. So this is going to become one of our go-to processes, is what I would say. Take the log of both sides in order, there's a reason why I do this, in order to get the exponent down. Okay, that's the rationale behind what we're doing, and we will do it over and over and over again. So when you get into the homework for this, it's like 4.4 in the homework. When you start working on that homework, you'll see, oh, they want me to take the log, take the log, take the log. Okay, so we're going to take the log of both sides. That's what we're going to do. The log of 4 to the x equals the log of 15. Okay. You don't always have to write the parentheses there, but sometimes it helps. And notice that I didn't write what base I'm using. Okay. So again, if I don't write a base, we know this is log base 10 or the common log. And your calculator, if you don't have a base and you don't, I'm not even going to show y'all how to do that craziness. But if you don't have a base, then your calculator is going to say it's base 10 also. Okay. So log of 4 to the x is equal to log of 15. Okay. And you're like, okay, what do? I can't punch that on you could punch log of 15 on your calculator, but you can't punch this one on the left on your calculator. So hopefully you remember the reason we're taking the log is so we can get that exponent down. So this is the log is an exponent and it's being raised to an exponent. And remember the rule is I can grab that exponent, move it to the front of the log, and write it as a multiplication problem, right? So this becomes x times the log of 4 is equal to log of 15. X times the log of 4. All right. Where log of 4 is going to give me a number. If you punch that on your calculator, it's going to be a crazy decimal. Okay. So I'm not caring about the crazy decimals. I don't want the crazy decimals. I'm just going to leave it as log 4. But this is a number and it's being multiplied by the x now. Okay. That's that rule that we're using. Bring the exponent down. I'm going to write it. Bring the exponent down in front. Oops, in front. And multiply. Okay, that's the exponent rule we're using. And once you have it rewritten like this, you can look at it and you go, oh, I can get x by itself very easily. X is being multiplied by log of 4. So how do I undo multiplication? I divide, right? So divide by log of 4. That guy's going to go away and it'll leave my x completely by itself, which is what I want. But remember, this is an equation, and what I do to the left-hand side, I have to do to the right-hand side. So I divided by log 4 here. I'm going to divide by log 4 here. So on the right-hand side, I have the log of 15 divided by the log of 4. Okay. I don't care what it says over there. I don't care if it's, log of 2200 or whatever. And we don't care necessarily what that number is unless they ask me to give a decimal approximation. What I care about is, look, there's only this one x here by itself and everything else is a number value, right? So these are things I can punch on my calculator and get a value for. So I've got x by itself. That's what I care about. Yay. What do we think? It's all right. Okay. Till I hear people say, no, I have a question. I'm just going. We got a couple more examples we're going to use. So, did everybody get a chance to watch the Friday video where we talked about log properties? I hope you got to watch that. Yes. Okay, good. Thank you. Thumbs up. Yay. So that one dealt with the addition of exponents, the subtraction of exponents and stuff like that. So some of these things are going to turn into a little bit more craziness. It's not going to be as nice and pretty as what this is, right? So I'm going to skip some exponential functions because I feel like most of these are the same. And I'm going to a logarithmic function because I want us to get some practice working with log problems. There we go. Okay. So I'm skipping over a little bit to log equations. So here's my example. It says, you've got the log base 4 of x plus 3 equal to 2. Okay. Log base 4 of x plus 3 is equal to the 2. Now look at this one. It's just like when I had exponentials and I had the variable was up here in the exponent. I got to get it out of the exponent. Now it's kind of the opposite. This is the inverse situation. I've got the x inside of a logarithm, right? And I've got to get it out of the logarithm. Well, I can't punch log base 4 of x on my calculator. I can't get a number value, right? So I've got the x. So the variable is inside the log. We need to get it out. Okay. And the way we're going to do that is by changing this to an exponential function. So change it to exponential function. Okay. And there might be extra steps that are involved with that deal with all those log properties that we did last on the video. So if you haven't done the log property video, make sure you watch it. But I'm going to do it using those properties, and sometimes it's complicated, sometimes it's not. So this one, I'm just going to use the basic definition. So remember that log base answer equals exponent. That's the format that this is in. So the base is a 4. The answer here the part that's going to be by itself is the x plus 3, and the exponent is the 2, right? So that's what the log guy looks like, and the exponent guy looks like base raised to the exponent equals the answer. So this is a problem where I need to rearrange stuff. Okay, so it looks like this. The variable is inside of the log. I can't do anything with it like that when the variable is inside of the log. So I need to pull it out. I'm going to do that by changing the way it looks. I'm going to make it look like an exponential function. Okay, so I come back here and I say, what was my base? Well, the base was the 4, right? So I'm going to change it into exponential here. Let me scoot, sorry. I'm going to change it into exponential here by putting the base at the bottom. 4 to the exponent is going to be right here. We know that. But in the log function, the exponent part is over here by itself. That's the 2. So 4 squared, right, is going to equal the answer part. Well, we said the answer part was all that stuff that's inside the log, right? So all that stuff inside of the log is the x plus 3. 4 squared equals x plus 3. Oh, look at that. I can work with that. Okay. So when it's in a logarithmic function and the variable's inside, and you're like, I can't do anything with that. A lot of times what you need to do is change it to exponential, and now boom, I can work with this. So 4 squared is 16, right? 4 times 4. 16 equals x plus 3. And sure enough, we can solve for x there, right? It's an plus 3, so we need to minus 3, right? Everybody agree? Get rid of the 3 over there. It's going to go away. And what I do to the right side, I have to do the left. So 16 minus 3 is 13. X equals 13. Okay. And I'm going to say the only thing you need to really double check for is that I've got a number that I can actually take the log of. So when I stuck this x equals 13 in here, 13 plus 3 is 16. Yeah, I can take the log of that guy, right? The things I can't take the log of in general in logarithm functions are these negative guys, right? So if I had x equals -1 and I tried to put it in, like if you punch in your calculator the log of -3, it's going to tell you it's an error because I don't get any values out there, right? So same thing here. This number needs to be a positive thing. If it's negative, I'm going to get an error. All right, and that looks like I've probably got 30 seconds left. So are we all right? We're not finished with 4.4. Yep, thumbs up, thank you. Yay, awesome. We're not done with 4.4, but we're getting close enough. You could probably start looking at that homework. But definitely you can do the homework for 4.1, 4.2, 4.3. All right. And I'll get you a quiz in there. Remember, I'm not going to be here on Monday. So you're not meeting with me on Monday. You're watching videos, and I'll send an email about all of that. All right. Any questions? Nope. You're out. Have a great weekend, I guess. I'll see you later.